Hi, it's Dr. T. I decided I would kind of give you a quick review of last Wednesday's lecture. We went quickly. I think that there's a lot of content there. And since one of the topics is going to be covered heavily on the quiz, I thought it'd be worthwhile kind of reviewing that. First, we talked about greenhouse gases, molecular shape, and molecular vibrations. And that was kind of a big piece of it. But what makes a gas a greenhouse gas is kind of be the first thing we talk about. Then you've already learned about how to determine molecular shape. We'll find out greenhouse gases require something about the notion of molecular vibrations, and then we'll go and take a look at some historical data, and that's really important because I want you to be able to interpret graphs and understand what the important things are to look for when you're interpreting a graph. So, back to the idea of what makes a gas a greenhouse gas. If you come back to carbon dioxide, turns out what makes a greenhouse gas is its ability to absorb and emit infrared radiation. For the carbon dioxide, you drew the structure out. We went through that, and here it is. It's got the linear structure, it's got bond angle of 180 degrees. Turns out there are three different vibrational modes that carbon dioxide can have. One of which is this symmetrical vibration, where both the carbon-oxygen bonds get longer and shorter at the same time. There are two other vibrations which do absorb and emit infrared. One is this asymmetric vibration, where one bond gets shorter and the other bond gets longer. The other vibration we deal with is this bending. It makes this carbon-oxygen bond angle goes from 180 to less than 180 degrees. So these two vibrations are why carbon dioxide is a greenhouse gas. Nitrogen and oxygen are not greenhouse gases because their vibrations are all this symmetrical type, like in carbon dioxide, which don't absorb infrared radiation. Methane and other gases have these asymmetric vibrations that are in fact absorbing and emitting IR, and they are also greenhouse gases. And they talk about those specific gases in your textbook. So, and if you want to know why that's the case, you could take quantum mechanics, but otherwise you can take my word for it. Quantum mechanics, it's more than a good idea. So let's take a look at some of these graphs, and these graphs are important for you to understand. And let's start off by taking a look at three big pictures of history. When you look at graphs, one of the important things is to look at what the axis labels are. This is a linear scale. It goes from 1960 to 2010, 50 years. We see the carbon dioxide concentration goes from under 320 parts per million to maybe close to 400. What do we see? We see kind of a smooth upward trend. Overlaid on that smooth upward trend, which is in black, is this red oscillation. So you want to know, is that gradual and normal? Well, it's gradually going up, but maybe that may be an artifact of how we're looking at data. What is this oscillation? Is that normal? Yes, that is normal. In fact, it keeps on happening. If we look at this oscillation, it's the short term. It happens every year, just like the seasons. And in fact, that's what the oscillations do to. During the winter, that's starting in October, carbon dioxide, the plants stop consuming carbon dioxide. So the carbon dioxide starts to build up in the atmosphere until springtime. Then when springtime happens, the plants start to consume carbon dioxide, and the levels drop down until the plants go back into hibernation for the winter, and the carbon dioxide start to build up again. And it happens year after year. So let's take a look at some take-home messages. On this scale, which is relatively short term, these 50 years, it looks like carbon dioxide is slowly going up. There are some short-term oscillations which are due to the seasons, and those are readily explained. So the next couple of graphs are a bit more complicated, a little more complex. The next graph, rather than 50 years on the horizontal scale, goes from 1000 to 2000 AD, and that's 1,000 years. If we look at this red dots up here, these red dots are in fact all a summary of all the data we saw on the previous chart. That's 50 years worth of data here. We can see now that what looked like a smooth gradual trend in that short period of time now looks like a pretty steep trend. And in fact, we can see that it looks like carbon dioxide was pretty steady, at least over a 1,000-year time period, until it got to about 1800, which is when the Industrial Revolution started. And population increased, and we started burning more fossil fuels and so on. And now we see this increase looks even a little steeper. But is this long-term, is this steady state? Has it always been this concentration of around 270 parts per million before the Industrial Revolution? In order to find that, we have to even look further back and deeper ice cores, and that is the Vostok Glacier data here. And if we take a look at this, we can see that, in fact, there are cycles. They have nothing, these have to do with astronomical cycles. Our planet changing its orbit, it's tilting its orbit, and we can see that, in fact, there are cycles. But in none of those cases do we see the concentration of CO2 exceeding 300 parts per million. If we look at this green and red data here, that seems to be like 1/4 of the data. We can see it's just a little fraction of this, because this is nearly 500,000 years of data projected here, and we can see that, in fact, this looks like a very steep increase, and it's much higher than the rest of this. So this suggests that there is some anthropogenic, humankind caught nature to this, because only at this point in time has the population of Earth exceeded billions of people, and we've been burning that much fossil fuels. Similarly, if we look at another greenhouse gas, methane, which is correlated with human activity, we can see that, in fact, over the course of 1 million years, basically the concentration never exceeded much over 700 parts per million. Only in recent times, again, correlating with high degrees of agriculture, increases in population, do we see that the methane concentration starts to go up past 700 parts per billion, and it seems to be rising very quickly. Again, on this expanded scale of 150 years, it looks pretty gradual, but in the geological time frame, it looks pretty dramatic. So it looks like humankind activity is, in fact, really having an impact. Again, remember that methane comes from things like livestock farming, rice farming. There's methane that's on the floor of the ocean in the form of clathrates. So next time we will come back and we'll look at this data, that we'll pick up these graphs, and we go back to that Vostok data, which is about 500,000 years worth of data, where we look at the CO2 concentration, which is in blue, and see how it correlates with temperature. If you look at the data and come back, we'll start thinking a little bit of how that looks like there's a pretty good correlation with CO2 and planetary temperature. So then from that point, we can come back and talk about, we'll talk about this, we'll pick up with that graph, and we'll see you there.